In the previous module, we have introduced complex numbers. We have seen that the real axis was not sufficient to represent new set of numbers, and we named that as imaginary numbers. And the notation that we have followed was j, and we named that as equals to under root of -1. So j here is an imaginary number that is defined as root of -1. We have also seen that using this imaginary number, we can come up with what are called as complex exponentials. We have also seen the relationship or the Euler equation that relates complex exponentials with the sinusoids. That relation says that if you have the complex exponential e to the power j theta, that can be represented as cos theta plus j sin theta. That's all about the complex exponentials. Now the complex exponentials are quite different from the normal exponentials. We are already aware of what are the normal exponentials. The normal exponentials have the form something like this. So if we have conventional or the normal exponentials, the normal exponentials takes the form as, say, x of t, let it be a conventional exponential. It takes the form as c e to the power at. This is a normal exponential function that we already know. But the complex exponential is having some different form. So this is a real exponential, you can say, xr of t, and a complex exponential has the form as c e to the power j at. Now it's easy to visualize these normal exponentials. These normal exponentials look something like this. So I'm just drawing a visualization for this normal or real exponentials. So they have this form something like this. So if we have this normal exponential, now we need to fix this c and a. Now let's say a, if it is greater than 0 or positive, then this signal looks something like this, where this crossing is c, and this is c times e to the power at for a greater than 0, and the axis is labeled as 0 here. Let this be t, and this is the signal. So I have drawn the normal exponential xr of t, that is c into e to the power at for a greater than 0, and for the a less than 0, the signal appears to be like this. So this is for c e to the power at, and for a less than 0, that is negative. Now we can easily visualize these exponentials, the real exponentials. But then how to visualize these complex exponentials, because this j is creating a problem here. We are not able to easily visualize this, the complex exponentials. Now for that purpose, we can take help of this Euler equation. We know that this Euler equation says that if we have the complex exponential, it can be represented with the help of two real signals, that is cosine and the sine, where the cosine part is the real part as well as the sine part here is the imaginary part. Now let's try to plot this. So I will use MATLAB platform to plot this signal e to the power j theta in order to visualize how this complex signal looks like. Now, for that purpose, what I will do is I will vary this theta from 0 to 2 pi, and I will try to plot real parts and imaginary parts separately and try to visualize this signal as a whole. Let's see that. I've written a couple of lines of program here. I'm varying this theta from 0 to 2 pi for 100 points, and I've simply plotted the graph of theta versus cos theta and sin theta. So if I run this, you can see this beautiful representation of the exponentials. This looks like a kind of spherical structure. Now let's interpret this. Now what we have plotted is the theta on the x-axis or this axis. We have plotted the theta or the angle. On this axis we have plotted the cos or the real part, and on the third axis we have plotted the imaginary or the sine part. If I try to visualize this, you can see that this is the representation of a complex exponential. Therefore, it must have the cos part and the sine part. But how to visualize that? We can see that if we project this complex exponential onto the real axis, we should be able to see the cos function. That means if I try to visualize this, so I will simply move this graph in a 3D in such a way that the mapping onto the real axis is seen. You can see that I've simply moved this graph in such a way that this mapping onto the real axis is seen. You can see that this is simply the cos signal. It's simply the projection of the complex exponential onto the real axis. So if I want to make it more clear, I will simply rotate this graph to visualize this real part, that is the cos part. So the same signal that was looking spherical in nature is now a pure cosine signal if it is being seen as a projection onto the real axis. Coming back to its original visualization, you can see that this again takes the same form of the complex exponential. Now let's look at the imaginary part. The imaginary part is again a projection of this complex exponential onto the imaginary axis. So I'll try to rotate this graph in such a way that you should be able to visualize the sine part. So I'm just rotating this, and I can see that this signal can be now visualized as a sinusoid. You can see that I'm just looking at the projection that this complex exponential makes onto the imaginary axis. So it's the same signal, that is the complex exponential, the projection of which we are looking on the real part and the imaginary part. See that this is a pure sinusoid. So this is the original complex exponential, and if you want to see the cos part, you just look atop of this graph. So you need to look at from the top of this graph and visualize the real part. So if I simply look at the top, you can see the cos function, and if I simply look at from the lateral side or from the sideways, you can see the sine function, and the combo of both of them will give you this complex exponential. Now if I try to plot the real part versus the imaginary part, that means suppose we need to plot a graph where the real part is on the horizontal axis and the imaginary on the vertical axis, let's see how it looks like. So we have seen, until now we have seen two projections. We have seen the top version, the top projection, and the side projection. The top projection will give you the cos part. The side projection will give you the sine part. One more projection is left, that is the real versus the imaginary. And if you look that, you'll be amazed to see that this is going to form a circle. Beautiful. So if we try to plot the real part versus the imaginary part, we'll get a circle. So that is the interpretation of the complex exponential, or the visualization of this complex exponential. Now if I play this in an animated way, I got some animations on the web. So let me show you how that animation looks like. Yeah, this image is available on this website. You can see that here I'm having the same complex exponential, but here that theta is getting varied. And as we vary this theta, we are having this spherical shape of complex exponential that is there in green. And if you look at the projection, that is the top view, the projection of this complex exponential onto the real axis, that is the top view, you can see this blue cosine function. And if you look at the projection laterally, we can see this in yellow is the sine wave that we are getting, that is the imaginary part. And if you look at the plot that we are getting, if we make the plot of real versus imaginary, we are getting a circle. So this is a nice animation that helps you to visualize the relationship between the complex exponential and the sinusoids. So coming back, we have seen the complex exponential. So we can now visualize what are and how this complex exponentials look like. So these are nothing but complex exponentials are having two parts, the real and the imaginary, and both of them are actually real. They are just separated by this notation, that is the imaginary notation, or J. Now let's look at these complex exponentials in signals and systems point of view. Now as I said, we are going to look at the complex exponentials where this theta is usually going to be the frequency and the time. We have already seen the sinusoids. When we have introduced the sinusoid, in parenthesis, that is this theta part is going to be omega t. That means e to the power j, this theta part is going to be omega t if it is a continuous time case, or it is going to be e to the power j small omega t, so small omega n, if it is the discrete time case. Now we have already looked into what are the frequencies in the continuous time case and the discrete time case. Let me quickly recapitulate those frequencies once again. We've already seen the frequencies of continuous time sinusoids and the discrete time sinusoids. For the continuous time, the frequency is being denoted as capital F, that can be varied all the way from minus infinite to infinite, whereas for the discrete time case, we have proved that the frequency of discrete time sinusoids are having the range from minus half to half. The angular frequency of continuous time sinusoids are denoted by capital omega, that is 2 pi into capital F. Whereas the angular frequency For discrete time sinusoids, we have denoted that by small omega, that is 2 pi times small f. Now we have got two different cases of complex exponentials, for the continuous time case and for the discrete time case. So here it should be n. For the continuous time case, we have the complex exponentials being represented by e to the power j omega t, where this omega t is the theta. We have already seen that. And this complex exponentials in the discrete time case is going to be of the form e to the power j omega n. Now there is very specific property of this complex exponentials. The main property of this complex exponential is that they are periodic in nature. So let me write that. The main property that actually distinguishes from the conventional exponentials is that the complex exponentials are periodic in nature. So let me write that. The complex exponentials are periodic in nature, whereas these are not. The normal exponentials are not periodic. We know how they look like. They look something like this, and of course they are not periodic. But the complex exponentials are periodic in nature, and we have already seen the visualization of them. If they are periodic, there should be a period, and that period can be easily measured as capital T equals to 2 pi by capital omega for the continuous time case. And this is very similar to what we have seen for the period of sinusoids in the continuous time case. Similarly, for the discrete time case, we have the period as capital N, that is 2 pi by small omega, but this is true only if this capital N is a ratio of two integers. That's because of the constraint of this small f. The small f need to be a ratio of two integers. We have already seen that this small f here is cycles per samples. And for this, the discrete time exponentials to be periodic, small f must be a ratio of two integers. And if that is the case, this capital N must be a ratio of two integers. Then only this discrete time exponentials, complex exponentials, are going to be periodic in nature. Let's look at some examples in order to understand the periodicity of complex exponentials. Example. Let's say if you have x of t equals to e to the power j pi t. Now the moment that we see this is a complex exponential, that too in the continuous time domain, we must conclude that this is going to be a periodic signal. And we know what is going to be the period. The period is going to be capital T, that is 2 pi by capital omega, and we know what is omega here. This omega is simply pi. So this capital T here is going to be 2. So this complex exponential is periodic with a period 2. So this is periodic with period t equals to 2. Let's take another example. So this is example 1. Let's take another example. Now let's take the example for the discrete time case. let's say x of n equals to e to the power j n by 4. Let's take this example. Now here we can see that this omega, the omega here is 1 by 4. So let me write that the omega, the small omega, just because this is a discrete time case, we have this small omega that is going to be 1 by 4, and due to this, the small f is going to be 1 upon 8 pi, that is an irrational number, and hence this capital N is not going to be the ratio of two integers. So capital N, as we have seen, it is 2 pi by small omega, that is 2 pi by 1 by 4, that is going to be 8 pi. It is irrational. Therefore, this signal is not periodic. The point that we should note here is that the continuous times exponentials, the continuous time complex exponentials are going to be always periodic. Let's take another example, say example 3. If you have x of t equals to e to the power j 2t. Now here omega, capital omega, is 2, and t here, that is 2 pi by omega, is going to be pi. So this signal is periodic. So there is no constraint of the rational number in the continuous time case. So this is periodic. The point to note here is that the continuous time complex exponentials are going to be always periodic, but for the discrete time case we have to be cautious. For the discrete time complex exponentials, we need to check whether this period is a ratio of two integers or not. If that is the case, then only we can find a period, otherwise we can't. If the period is not a ratio of two integers, the signal is going to be non-periodic. We shall see more into the complex exponentials in the next module. See you then.